Right. In this video, I'm going to be working some examples about the definition of the derivative. But I'm just going to tell you right now, if you came here looking for examples where we compute derivatives of specific functions using the definition and using all the algebraic steps, this is not the right video for you. Okay, this is just like definition of the derivative, interpreting the derivative, distinguishing between average and instantaneous rate of change, stuff like that. Okay, so the first one is the temperature of an oven at time t is given by h of t degrees Celsius, where t is measured in minutes after the oven began to preheat. Using correct units, interpret the equations h of 10 equals 150 and h prime of 10 is equal to 15 in the context of the problem. All right, so when we say h of 10 equals 150, okay, that means that at t equals 10 minutes after the oven began preheating, the temperature of the oven is 150 degrees Celsius. Okay. Then h prime of 10 equaling 15, that means that the rate of change of temperature with respect to time is 15 degrees Celsius per minute. Okay, so at time t equals 10 minutes, temperature is changing at a rate of 15, and then the units of the rate is units of h divided by units of t. So degrees Celsius per minute. All right, now let's rank f prime of 2, f prime of 0, and f prime of 3 in order from least to greatest. Okay. Oftentimes in this class, you're going to be asked to rank 3 things in order from least to greatest, and one's going to be negative, one's going to be 0, one's going to be positive. Just telling you that's how this is going to go frequently, and this is one of those situations. So I'm going to say f prime of negative 2 is positive because the slope of the graph at x equals negative 2, it's positive. Okay. At x equals 0, f prime of 0 is 0 because you would think that, yeah, the tangent line is going to be horizontal at that place. All right, and then at x with 3, f prime of 3 is going to be negative. And, okay, yeah, so that means that if I'm going to order from least to greatest, it's going to be f prime of 3 is less than f prime of 0 is less than f prime of negative 2. All right, now, number 3, if the line tangent to the graph of f at the point 1, 7. Okay, well, that tells me right now that f of 1 is equal to 7, right? If that's the point C, then that point is on the graph of f of x, right? So f of 1 is equal to 7. F prime of 1 is equal to the slope of the tangent line. But I've got one point on the tangent line and another point on the tangent line, and we know how to find the slope between 2 points. So I'm going to take y2 minus y1 divided by x2 minus x1. Okay. And that's going to be 2 minus 7 is negative 5 over negative 4, and so that's 5/4. Okay, we want f of 1 plus f prime of 1. And, this would make like a really good multiple choice question. That would be 7 plus 5/4. 7 is 28 over 4, and 5 is 33 divided by 4. All right, here we're seeing if g of 3 is 4 and g prime of 3 is 5, write an equation for the line tangent to the graph of graph of g at x equals 3. Okay, we can do that. If g of 3 equals 4, then that means the point the point of tangency is 3, 4. Then my slope is g prime of 3 equals 5. So my equation is going to be y minus the y-coordinate of the point that we know is on the line is equal to the slope times x minus the x-coordinate of the point that we know is on the line. Okay? That's how we write the equation for the line tangent to the graph. When, especially, for the most part in this class, we're going to have to do some work to find this, maybe this as well. But if this is given to us, it'll be nice and easy to write it down. All right, number 6. Suppose g of x is a piecewise function divided by g of x is 3x minus 2 when x is greater than or equal to 3, but g of x is equal to 7 when x is less than 3. All right, find the values of g prime of 0 and g prime of 5. Okay, well, 0 is less than 3, and we know that the derivative of a constant is going to be 0 because the graph of a constant is a flat horizontal line. So this is the derivative with respect to x of 7 at the point where x equals 0. Now, the derivative of 7 is the same no matter where it is, because the graph of y equals 7 looks like, okay, this is where x is less than 3. Say it like that. Say this is 7, it's flat. Okay, so it's horizontal, meaning that the slope is 0. Then g prime of 5, it's 3x minus 2, which would be 9 minus 2 is 7. Oh, that's convenient. So it goes right there. Okay. G prime of 5 equals the derivative with respect to x of 3x minus 2 at the point where x equals 5. Now we know that the slope of 3x minus 2 is the same everywhere. It's always 3. So this slope doesn't matter if it's x equals 5 or anything bigger than 3. That value is going to be 3. And for part B, is g at x equals 3? Yes, because the limit as x approaches 3 from the negative side of g is equal to 7, and the limit as x approaches 3 from the right of g is equal to 3 times 3 minus 2, which is also equal to 7, and the most important part, g of 3 is also equal to 7. That's what makes it continuous. You can also see that here. I already drew the picture. And then part C, no. This is not differentiable. Okay? On one hand, you could say the graph of g has a sharp corner, but you are really given the graph of g. So I'm going to give my reason in terms of what I was given. And remember that the differentiable means that g prime of, say, 3 exists. Okay, well, g prime of 3 would equal the limit as h approaches 0 of g of 3 plus h minus g of 3 divided by h. But, okay, as I approach this from the left side, okay, that limit is 0. And as I approach from the right side, the slope, which is what this limit represents, that's equal to 3, right? Because the slope from the right is 3, the slope from the left is 0. I need those to be the same in order for me to have like a smooth, nice slope where I could lay in a tangent line. But if you said no because there's a sharp corner on the graph, you would be just fine. I have to get a new sheet of paper. Unfortunately, on this one, the hole punch, it drove right through part of the question. But I looked up the original. It's on the closed interval 0 to 10. So the average rate of change of f is going to be f of 10 minus f of 0 divided by 10 minus 0. And that's going to be negative 20 minus 5 over 10 minus 0. And that's a perfectly fine place to stop in this class. You know, if you want to make that negative 25 divided by 10 is negative 2.5, good for you. If not, just move on. All right. Now, the graph of f is pictured at left to give the values of k that make the statement true. Okay, basically this is asking where is f undefined? What are the x values where f doesn't exist? And I think that's going to be 6. So 8a is k equals 6. For b, it's going to be, okay, where does the limit not exist? That's at negative 1, right? I'm approaching two different things from the left and from the right. For c, the limit exists but is not equal to the value of the function. Okay, that would be, I guess that's going to be 6 because it's not f of k is not defined where k equals 6, so, it can't be equal to something that's undefined, especially if your limit is existing. I guess what I would say, a better one would be, let's just say I wanted 2 to be the answer to that. If I had a little hole there, and then I filled it in like up here, that would be, so. In that case, then we would add k equals 2 to this list as well. Okay? But that was not the way that the graph looked, actually, so I'm going to just go back to the way it was, and for part D, because then I don't want anybody to be confused. Okay, for part D, f prime does not exist. F prime doesn't exist at a sharp corner, a vertical tangent, or any place where there's a discontinuity. So that's going to be k equals -1 and k equals 6. Okay, but I don't see any other sharp corners. The only way you know is if there's a vertical tangent is if they tell you. You're not going to ever just look at a graph and be like, oh, I think that's vertical. They will tell you explicitly, hey, there's a vertical tangent here. All right. Number 9 is, here's the graph, sketch its derivative. Okay, and we can do that. This is going to be very approximate. Okay, over here, the slope is negative. Okay, so it looks like it's more negative over here than there, but that is not a consideration you really need to be able to make. I don't need you to do that at this point. So it's, I don't know, maybe it's like that. But here I've got a sharp corner, or something that really looks like a sharp corner to me, so I'm going to assume it is sharp. And if it's sharp, the derivative is undefined. Okay, so I'm drawing f prime here. But then over here, all of a sudden, it goes immediately positive, right? So I'm going to say it's positive to 0 to negative. So, I don't really know, but maybe something like that. Or no, I guess it ends here, so I'd put a dot. That's my idea of the derivative. But the idea needs to be that it's negative, undefined, positive, 0, negative. Okay. And over here at G, it looks like I have flat tangents at 1, 2, and 3. So I'm going to make sure that those are zeros of my derivative. Okay, before 1, it's positive. Okay, between 1 and 2, the slope is negative. But at 2, the slope goes back to 0, so maybe it's like that or something. I'll make it smooth, because I don't know that the first derivative has a sharp corner. We can't really tell that from looking at the graph. Then here it's positive slope, then it goes back to 0 slope, so it's probably like that. And then after 3 and up to 4, the slope is negative, and it seems to be getting more negative, so maybe I'll just say it's like that. And then to draw h prime, all right, this is going to be, all right, at 2, I've got a 0 slope, so h prime equals 0. That's where I want to start. To the left of 2, the slope is positive, and to the right of 2, the slope is negative. So maybe I'll say it's like that. Maybe this is 4. Okay. At 4, there's a discontinuity, so h prime had better be undefined. Okay. And then after 4, the slope of h is constantly negative. Now, I feel like this slope is less steep than the slope right here, so I'm going to make this constant negative, but less negative than it had been. And these two open circles are supposed to be right over each other. I don't think I might have missed the mark in that regard, but that's all right. That's us drawing the derivative given the original, and I think number 10 is going to be the opposite. Here's the derivative, draw the original. Draw something that could be the original, right? Yeah, so let's start with, okay, there's f prime. Let's sketch the graph of f. Okay, well, I'm going to call that 0, and I'm going to call this 8. So the zeros of the derivative in this case are 1, 3, and 6. So those are going to be important points because the tangent is going to go flat there. All right, and what's going to happen here? I'm going to, okay, f is got a negative slope before 1, and then it's got a 0 slope, and then has a positive slope between 1 and 3. So maybe it's like and a 0 slope at 3, and then the slope becomes negative here between 3 and 4. Okay, I lost myself. Okay, yeah, and then the slope is negative, and then maybe this is 4. It suddenly goes positive, right? The slope suddenly goes from negative to positive, so that's going to be a sharp corner. Okay. And then at 6, I've got a 0 slope, so I've got that, and then from 6 to 8, I've got a negative slope. And yeah, it's a little tough, right? It's the discontinuity was what, and again, this is, probably should have that, right, to match the original. Okay, if that's G prime, this is the zeros of G prime, so I'm going to say, well, it looks like, we'll say it's there. And then G prime is negative, 0, positive. So I go from negative slope to 0 slope, to positive slope, back to 0 slope, back to negative slope. Negative slope here, okay, 0 slope. Positive is through here, 0 slope again, and then negative slope after that. And, okay, this one, so this was the graph of F, this is the graph of G, this is going to be the graph of H. Looks like the zeros are at, I'm just going to assume that's 3 and negative 1, which is like right there. So I'm going from negative slope to 0 slope, to positive slope, back to 0 slope. And then afterwards, I'm going negative slope. I want that to be smooth. All right. That's me drawing the graph of the original given the graph of the derivative. Okay, now I'm going to record solutions to the extra practice. All right, so we've got a graph right here. We've got some points labeled. Just a couple of tools here. And we're going to determine whether the quantities are positive, negative, or 0. Okay. F of A, that's the height of the graph of y equals f of x at x equals a, that's 0. Okay, f of B is positive, f of C is negative, f of D is looking positive. Okay. F prime of A represents the slope of the graph of f at the point where x equals a. Okay, that's got positive slope there, so I'm going to say it's positive. At B, I've got negative slope. At C, it looks like I've got 0 slope. And at D, it looks like I've got positive slope again. Okay. Now this limit here, you need to recognize that that's code for the slope of the graph of f at the point where x equals b. So that's f prime of b. Again, that's the slope at b. That's negative. Okay. This is a different form of the limit definition of the derivative, but it is, one of our forms of the definition of the derivative. So this limit is equal to f prime at d, and that's a positive number. Okay. This, just difference quotient with no limit, is going to be the slope between points A and C. Okay. This is the average rate of change of f over the interval A to C. And so what you do is, you connect these two dots, and you see that that's got a negative slope. So average rate of change on the interval A to C. And I'm not going to write that for this one right after, or maybe I will. And that's negative. Okay, this is the average rate of change on the interval B to D. Okay, well, on the interval B to D, right, we're seeing a positive slope there. Okay, so we're going to say that that average rate of change is positive because the average rate of change represents the slope of the secant line. Number 13, this is f prime of c. It's the slope of the graph of f at x equals c, and that's 0. We kind of already said that once, yeah. And this is f prime at x equals a. Okay, this slope at a, that's positive. Okay. The limit as x approaches a of f of x, okay, what's happening to f of x as x approaches a from both sides? I'm approaching y equals 0. So I'm going to say that limit is 0. Okay, and then the last question, and this is not something I'm going to determine whether it's positive, negative, or 0, but how many values of k satisfy the equation limit as h approaches 0 of f of k plus h minus f of k divided by h equals 0? Well, you just have to say that this is code for f prime with k plugged in equals 0. It's saying how many places is the slope of f equal to 0? How many x values, right? This is where we put x values. So I've got 2 places, right? I've got here and I've got here. That's where the slope is equal to 0. So that's 2 places. There are 2 values. Okay. I've got another graph for you. I'm going to ask you, where is g prime of x undefined? Well, a derivative is undefined any place where the function has a sharp corner, a vertical tangent, or a discontinuity. Okay, so g prime is undefined right here at x equals 2, but also here at negative 2 where there was a discontinuity. Okay. For what values of k does the limit of g of x fail to exist? That would be right here, right? We've got a jump discontinuity right here. We've got differing behavior as we approach from the right as we approach from the left. So that's going to be k equals negative 2. For what values does this fail to exist? That's like saying, where is g prime undefined? Okay, so that's going to still be x equals 2 and negative 2. But you just have to recognize that this limit of the difference quotient as run goes towards 0, that represents g prime. Okay, it represents the slope of the tangent. And for what values of x is g of x undefined? That's x equals negative 2 only. Okay, g of x is well defined at 2, right? It's right here, g of 2 equals 0. Okay. Give an estimate to the nearest tenth of a value of x0 for which the slope of f at x0 is 0. So where is the slope equal to 0? Okay, well, I can find it. It's, right there and right there. Okay, now, I might ask you a question like this on the quiz, and if I ask you to round to the nearest tenth, I'm going to give you quite a bit of leeway, right? I think that on this one, you should be able to see that the bottom is, or the very bottom of this curve, this is happening to the right of this dotted line. Okay, so it's got to be bigger than 1.0. But it looks pretty close, so I'm going to say, x0 equals 1.1. But if you had said 1.0, 1.1, 1.2, even 1.3 or 1.4, I think that would be all right. 1.4, I'm going to kind of be doubting you on that because it's really not even close to halfway. But, on the quiz, we'll be pretty generous as far as what we're going to give credit for. Okay, and then the other value, that seems to be, over here where x is a little more negative than negative 1. Maybe I would call it negative 1.1. Okay, but if you called it negative 1.2, I would think you were just as right. Okay, and that's going to be all the example problems I've got for this video.